All right, this is AP, AB, and BC Calculus. We're doing Unit 7, Section 6, which is finding general solutions using separation of variables. Okay, so differential equations fall into two really broad categories, separable and non-separable. In this class, we're going to learn how to solve separable differential equations only. So later in college, you'll learn how to solve certain types of non-separable differential equations. So what makes a diffie-q separable? Well, if the expression only includes one variable, like just x's or just t's or just y's, it's separable. If the expression can be written as a product or quotient of the x's and y's, or y's and t's, or whatever the variables are, just products and quotients, then the equation is separable. If the expression has a sum or difference of multiple variables that is non-factorable in any way, then it is non-separable, right? So that's sort of what we're going to be looking out for. So let's go ahead and look quickly at a few of these. So separable, right? So this only has x's. This is separable, right? In order to separate this, what I would do is I would bring the the dx over rather, and I'd have dy on one side and all of this stuff times dx. This is separable. In order to separate this, I would bring the dx over and I would divide by the 3 minus y. This is separable. In order to separate this, I'd bring the dx over and I would multiply the y over, so I'd have all the y stuff. This one might not look separable at first, but it is, because if you factor it, it is y stuff times a bunch of x stuff, and I can bring the y stuff over, and I can bring the dx over with the x's. And then this one's the same one I wrote at the top. Sorry. Sometimes my brain is a little bit slow. Now, these are all non-separable over here, right? See how I have a sum of x and y, right? Or I have a difference of x stuff and y stuff. It's not factorable. Here I have a quotient, but in the quotient there's just sum and difference of x and y stuff. And here the x and y is a product, but it's inside another function. So these are all non-separable. To be clear, the AP can't ask you to solve these. So you can't be asked to solve non-separable diffie-qs. Now, eventually, you're going to take classes that you are able to solve non-separable differential equations of some categories, but for right now, you can't be asked. They can ask you to do math with them. They can ask you to differentiate them, right? I could ask you to differentiate and find d squared y dx squared. I can ask you to do other things with non-separable differential equations, but I cannot ask you to solve them. So that's important information, right? So when you see something like this differential equation that might look simple, but it's not simple to solve, you need to keep in your head, oh, hey, the AP can't ask me to solve this, right? So what does it mean to separate a differential equation? So I kind of already cheated and showed you a little bit here, but we're going to walk through it anyway. So what it means is that you split up the dy dx by multiplying the dx over to the other side. Now, usually that's the right-hand side on my equation, and the dy stays on the left-hand side, and then you use multiplication or division to get all of the y functions over to the left-hand side with the dy, and all of the x functions over to the right-hand side with the dx. So essentially, what your separated differential equation looks like is some function of y times dy and some function of x times dx. Now, it doesn't always have to be an x and a y. It could be a y and a t, or an a and a t, or a p and a q. It could be any of these things. But usually it's x and y, or it's y and t, or it's x and t, right? So here's a couple of examples. dy dt equals t cubed plus 4. To separate this, I would multiply the dt over, and I'd get dy, which is all my y stuff. So here the function of y is just the number 1, right? Like there's a 1 technically there. And then a function of t times dt. dy dx equals x squared. Well, I'm going to multiply the y over, I'm going to multiply the dx over, and I'm going to get y, which is the function of y, times dy, and then x squared times dx, function of x times dx. Here, right, I'm going to multiply the dx over, and I'm going to divide the 3 plus y over, and sure enough, what ends up happening is I get that I have a function of y, and if you need to see it this way, you can see it as this, function of y times dy dx equals a function of x, which in this case is just a 1 times dx, right? That's how we separate differential equations. So, moving on, we're not going to solve these, we're just going to separate them. So, I want to multiply my dx over, and I want to divide any y stuff over. So what's going to happen is I'm going to get dy over y plus 1 is going to equal an x cubed times a dx. This is separated. I don't want you to solve it yet. I just want you to separate it, okay? We're going to spend some time solving it later. All right, so we're going to separate this one. Again, pause me if you want to do it without me. So the dx is going to get multiplied over, right? And the y squared is going to end up on the bottom over here. So I'm going to get dy over y squared equals sine x dx. Notice it is important that the dy and the dx are on the top, right? So dy is on the top of this side, dx is on the top of this side, because if there's no fraction at all, then everything's on the top. So once we've separated the differential equation, we solve by integrating both sides, right? We find the antiderivative of both sides of the equation. Because c is an arbitrary constant, you only need the plus c on one side. You usually put it on the side of the independent variable, which is usually x or t, right? So this is called the general solution to a differential equation. If you're asked to do so, you should solve for y, but you're not always asked to do so. So generally, the way you're asked to solve for y is you're going to have some sort of phrase like y equals f of x is a solution, and that's telling you, hey, solve for y, right? That's saying you should have y equals a bunch of x stuff, right? Y should be a bunch of x stuff. That's the hint to solve for y. So if you're given what's called an initial value, you'll likely be asked to plug in and find the actual value of c, which gives you the particular solution to a differential equation. We're going to go ahead and do that in 7.7, which is not this video. So right now we're just finding general solutions to differential equations. All right, so let's go ahead and find the general solution. So the first thing we have to do is separate the variables. So I move the dx over, I get dy equals 2x plus 3 dx. If you don't separate the variables on an AP, you instantly get 0 points on the problem. If it's solving a diffie-q and you don't separate the variables, you get 0. So please, if you're asked to solve a diffie-q, separate the variables. Now I'm going to integrate both sides, right? I'm going to use the antiderivative for both sides. So when I integrate dy, I just get y, right? I don't need the plus c because I'm going to put the plus c on the side with the x. And then I'm going to get, when I integrate 2x, I'm going to get x squared because it would be 2x squared over 2, so I just get x squared, plus 3x plus c. And this is already solved for y, right? So I'm done because this is the code for solve for y. But again, in this case, it's already solved for y, so I don't have to worry about it. And that's my general solution. All right, you're going to go ahead and try one. So find the general solution to this differential equation, right? So pause me if you want to do it without me. First thing I'm going to do is separate the variables by moving my dx over. So I'm going to get dy equals cosine of x dx. And then I'm going to integrate both sides. So dy just integrates to y. I don't need the plus c. The antiderivative of cosine is sine, right? If you integrate cosine, you get sine plus c. And that's it. And it's already solved for y, so I'm done. All right, let's get a little bit trickier. So we're going to find the general solution to this differential equation. Again, this is code for solve for y. So when I'm done, I have to solve for y. So let's separate my variables. The y squared is going to come over, right? I multiply that over, and the dx gets multiplied over. So I'm going to get y squared dy equals e to the 2x dx, and I'm going to need to integrate both sides. So this becomes a y cubed over 3. I don't need the plus c because it's going to go on the other side. Now this is technically u sub, right? This is u sub where your u is 2x, but if you're able to logic through it, so if you need u sub, if you need to say, hey, u is 2x, so du is 2 dx, and so I'm going to have a du over 2 where my dx is. Hey, this is the integral of e to the u times du over 2, which is a 1/2 times this. If you need to get that this is a 1/2 e to the u plus c, like if you need the u substitution for this, I am not judging and that's fine. But if you're able to just look at this and understand that when you integrate e to the 2x, just like if you differentiate e to the 2x, you'd be multiplying by 2 every time because of the chain rule. When you integrate e to the 2x, you have to divide by 2. So if you can just jump here and get to this, nobody thinks you're cheating. So if you need this, then by all means do it. If you don't need it, then please don't and just integrate correctly and that's fine. Okay, so that's great. Okay, so this is correct, but remember up top there was that code that said solve for y. So now after I've done the correct answer, I need to solve for y, right? So I've done the correct answer, but I need to solve for y. So I'm going to solve for y by multiplying the 3 over. So I'm going to get y cubed equals 3/2 e to the 2x. And then I'm going to show you a little bit of a trick. I'm going to write plus c sub 1. the reason I can write that is because 3 times c is some new constant. And I don't have to call it c sub 1, I can just call it c if I want. But if you want to make it clear that it's a different c, call it c sub 1, that's fine. But 3 times an arbitrary constant is a new arbitrary constant. Right? To solve for y, I'm going to take the cube root, so I'm going to get that y is the cube root of this entire thing. 3 halves e to the 2x plus whatever that c sub 1 is, and that's my answer. Okay, so I had to solve for y. And the reason I had to solve for y is because in the question, I was specifically asked to solve for y. You're not always going to be asked that. Don't do it if you're not asked to do it because it makes your life harder for no reason. All right, so this is another one where you're being specifically asked to solve for y. Please pause me if you want to try it without me. So the first thing I do is separate my variables. I'm going to do that by dividing the y over and multiplying the dx over. When I do the antiderivative both sides, when I integrate dy over y, I get natural log of the absolute value of y. On the other side, I'm going to get an x cubed plus c. So this is correct, right? This is correct, but I have to solve for y. So in order to get rid of the the natural log, I'm going to exponentiate both sides. And this is where a little bit of a trick comes in. So you're going to find that it's most useful not to leave this as an e to the 3x plus, to the x cubed plus c. E to the x cubed plus c is the same as e to the x cubed times e to the c. Well, I can rewrite this as a new c, right? Because e to a constant is just some new constant, right? It's just a number. E is a number, so e to a number is a new number. So I'm going to rewrite this as y equals c sub 1 e to the x cubed, right? Now, you might say, why did I get rid of the absolute value? Good question. So why no absolute value? Well, the reason is because c sub 1 can have whatever sign it needs, right? So while this expression was originally written so it would have to be positive, right? It doesn't necessarily have to be positive because I don't know what c sub 1 is. C sub 1 could be a 5, it could be a -5, it could be a 208, I don't know what it is. So I don't need the absolute value because this c sub 1 is an arbitrary constant that could be positive or negative depending on the initial value I'm given. So this is the way you're likely going to see this, right? Let's go ahead and keep moving. All right, so we're going to find the general solution. Now, what I want you to note here is that there's no y equals f of x comment, right? They didn't say that, right? So I don't have to solve for y. So I don't have to solve for y. And if I'm not asked to solve for y, I probably shouldn't. So let's go ahead and walk through this. I'll make the marker a little thinner. All right, so I'm going to start by separating my variables. So dy over cosine squared of y equals a 6x dx. Now, I don't know about you, but I'm thinking, oh no, I don't want to have a cosine squared in the denominator. That's awful. I'm panicking. And then I realized that there is a trig identity that hopefully most of us know that says that 1 over cosine of theta is the same as secant of theta. That makes me realize that this side is actually just a secant squared y, and I feel a lot less panicked because I recognize that secant squared is an antiderivative rule. The integral of secant squared is tangent, right? Because if you differentiate tangent, you get secant squared. On this side, when I integrate, I'm going to get a 3x squared plus c, and that's it. I wasn't asked to solve for y, so I shouldn't solve for y. That's my answer. Yay, I'm happy. All right, one last problem. Go ahead and try this one. So again, note that here, it doesn't say y equals f of x, so you don't have to solve for y. And you really shouldn't, right? So you shouldn't do more work that you're not asked to do because you just risk making a silly mistake. So I'm going to divide the cosecant over. So I'm going to get dy over cosecant y equals e to the 3x dx. Now, again, same trick is to notice that 1 over the cosecant of theta is the same as the sine of theta. And if you remember that, it's going to make your life a lot easier because you're going to realize that this is actually the sine of y dy, which is way less stressful. And on this side, I have an e to the 3x dx. So when you integrate sine, right, the antiderivative of sine is negative cosine of y. And on this side, if you can just jump to this being a 1/3 e to the 3x plus c, that's great. If you don't feel like you can do that, right, if you need the u sub, you can say u is 3x, du is 3 dx, so your du over 3 is your dx. That makes this the integral of a 1/3 e to the u du, which is how you get 1/3 e to the u plus c, which is how we get the 1/3 e to the 3x plus c. If you need this, fine. So if you need the u sub, fine, right? Do it. But you're going to find, I think, a lot of times that when u sub is more straightforward, when the u is something like just a multiple of x, a lot of times you can do it in your head. Again, that's mostly a personal ability, like a personal preference, whether you need to do it or not. Just make sure you do the right thing to get the problem right. I don't need you showing random extra work.